All right, I'll begin with a word of prayer. Dearly Father, we thank you for the summer just completed, and we thank you for this class, this opportunity we have to meet together and to study algebraic topology from Rotman. We thank you for this text, for the wisdom of the author, and we just pray that we wouldn't do too much harm to it in our discussions. Lord, I pray. Amen. Yes, as I have warned you, I am not an expert, but I will do my best to try to walk through these things with you guys as fast as I can. So we're starting chapter 0. Again, Introduction to Algebraic Topology. Introduction, of course. So whatever it says up here doesn't matter. Introduction. So it's for undergraduates. Of course. All right, so.
Undergraduates can take graduate courses.
Well, not here. We don't have. We don't have a graduate math. Yeah. Undergraduates. Wait a minute. You're blowing my mind. Undergraduates can take graduate courses.
Actually, didn't realize it until I went to grad school.
Yeah. No, I took many graduate courses as an undergraduate. Yeah. It was. In fact, probably the best courses I took as an undergraduate were graduate math courses. Honestly, now that you bring it up, you get my pitchy thing. Make this. You notice that it kind of smells like an Asian market out in the hallway now. Like there's the very strong odor of sort of old half-cooked fish or something. I mean, the food court that has opened up down there, it is wafting. I mean, I prefer it to the smell of fresh paint, which is more often what sort of fills this hallway, but... Alright. You guys know what integers, rational numbers, complex numbers, you know, we use...
Mass for numbers, which of course the chapters of this book are indexed by.
He doesn't take a stand on n, does he? Huh, interesting. Alright, since, whatever. So notation, just a word. I guess I don't need this shining in my face. Of course, R is the real numbers. I is the interval from 0 to 1. More importantly, to this discussion, well, I guess we should talk about this. Our n tuples. The length of a point in X is what? It's he uses Euclidean length, so it's the square root of the sum of the squares. Alright, just getting this started. And, it's funny, I hadn't thought about this, but the 1 norm and the 2 norm, they're the same as they, go to one dimension. You ever notice this? So like in R2, this is of course the 2 norm, right? It's the Euclidean norm. But the 1 norm, it's some of the absolute values.
Yeah.
But it's kind of, I just noticed it's kind of weird. Well, I don't know. I guess I noticed this before at some point in my life, but the weirdest things amuse me. I don't know. Anyway, so Sn is the n sphere, right? And so this is x in Rn such that what? Yeah, equal to 1. And and then he starts talking about how he views different copies of Rn embedded in Rn plus 1 and so forth. And he's very, very slick about this and very fast, and it's great. For example, he basically says Rn is, a subset of Rn plus 1 under the identification what? Basically, Rn is just the subspace of Rn plus 1 consisting of all n plus 1 tuples with last coordinate 0. All right? And of course, Sn is the n sphere, radius 1, center of the origin. Let's see here, a bit more. He says you also can regard Sn as the equator of Sn plus 1. All right, so how's that go? How's that go? So here's the formula. Sn equals R Rn plus 1 intersect with Sn plus 1, right? And in terms of an actual, set builder comment on this, what is that? That's x1. Oh. Oh. Oh, it's this is very sneaky. Where is that space?
Isn't it Rn intersect Sn plus 1? Or
No, he means what he says.
okay.
You notice S.
Oh, this
Oh,
is
and maybe
this
it's
is
in-
And I think
Rn
maybe
plus
I have a typo, right? Yeah, I got a typo. Where's my typo?
Should be Rn plus 1.
Right here, right?
Yeah.
Yeah, very good. Otherwise, like we know, we say S1 is the unit circle, it's in R2, for example, right? I mean, there are other nomenclatures out there for indexing spheres, but this is the one we use. All right. So this this is the Rn plus 1 in Rn plus 2.
Mm-hmm.
All right, so this is actually like x1, x n plus 2 in, I can't do anything, in Sn plus 1 such that the last coordinate is 0, right? Let me draw them while I can. So, for example, here's the picture for S2, right? You have the, oh, maybe I can't do S2. S1, I'm not very good at drawing S3. So S1, here's S2, right? And here's X3, X2, X1 in the usual picture. And then if you set the last coordinate equal to 0, that's it. So I just drew a picture of S2, of course. And then S1 is this guy. Oh, well, man. I guess I have to. Anyway, you get the idea. So there's my S1 sitting inside R3, which is appearing at the intersection of S2 and the XY plane, otherwise known as R2 in R3. All right. Nothing terribly shocking here, of course. Mostly just setting up notation. Now, dn, right? What is dn in this? dn.
Set the disk.
Yeah, the n disk. So what this is going to be is x in Rn, such that the modulus is the length of x. Thanks, Nathan. Was that a fruit fly? What was that? I feel like I just. Ugh. Sorry, I gotta chew some gum now. I don't know what. I hope I just ingested marker dust. I'm not really sure. Something unpleasant. Yeah. Right. So there's the n disk, right? Or n ball. And so what are the inclusions we have here? We have S, n minus 1, a subset of dn, which is a subset of what? Right. Alright. At this point he introduces the standard n simplex, right? And I'm not really doing anything with that in this section, so I'm going to just skip it. He also mentioned there's a standard homeomorphism, from Sn with the north pole removed to Rn, called the Stereographic Projection, right? And he derives the formula for it pretty nicely here on page 2. It's a terribly efficient derivation. I think I'm actually going to go through it. So, stereographic projection. Let's talk about it just for a minute or two. So it's allegedly a homeomorphism from what? From Sn, with the North Pole removed, right, to Rn. And that we're going to call this map sigma. So I think, let's see here, I'm trying to remember what's a nice picture for this. Maybe this, I don't know. So here's Sn, right? Here's the North Pole. And what I can't remember is where I should put Rn. Is the circle resting on Rn, or is it
It's
going through?
isn't it the equator?
You can do either, I think.
You can do either. That's true, but we're doing one or the other here. Yeah, I think this one's the equator, but I have, you know. All right, so the mapping geometrically is described as follows, right? He says what you do is you say define sigma, all right, to be the intersection of Rn and the line joining x and n. All right, what he's really saying is define sigma x, all right, to be intersection, right, of, let me stop using this red, no one can see it, the intersection of, I can barely see it, intersection of x and line, I'm an idiot, intersection of Rn and line joining, what is it, x and n. Okay, so x is a point on the deleted n sphere, right? So x is something like, say here. And then, so you take a line, like that, and that is sigma of x. Okay, so what's the formula for sigma x then? Well, he points out, he says points on the line have the form what? What's a typical point on that line look like?
N plus t times x minus n.
Yeah, I think so.
Okay.
See, he writes it, he says it's tx. He starts the line at, I guess he makes x equal to 0, t equal to 0x, so he's like tx plus 1 minus t times n. Wait, I think
Or
it's
t
the same.
equals 1 equal x.
What's that?
When it's x when t equals 1.
Exactly,
Yeah.
when x, and so the point we're after, right, is when the last coordinate, so this is Rn, right? This red line is Rn, that's when the last coordinate. So, so this thing, what does this look like actually? This looks like, you know, tx1 plus 1 minus t times the first coordinate in the North Pole, right?
Which is 0, right?
Which is 0, right? Thank you. Yeah, duh. And so forth. So it's just tx2, all the way to tx what, n, and then the last thing, the n plus 1th is what? Txn plus 1 plus 1 minus t. Oh well. Plus 1 minus t. Sorry. It gives me too much amusement to do this. But anyway, so what we're really looking for is txn plus 1 plus 1 minus t, right? Because the n is, after all, what? I mean, it's 0, 0, 1, right?
Right, so that's be 0.
So this has to be equal to 0. So that tells us which parameter we need to pick on that green line in order to find the point sigma of x we're trying to construct the formula for. And so you can solve for t, right? I asked a pretty analogous algebra question to Calculus 2 on the quiz yesterday. I did that. Not with the x of n plus 1, just with a's and b's and stuff. Yeah, I did that. Alright, so t, what we got is we've got t equals to 1 over 1 minus xn plus 1, which of course is well defined on the deleted n sphere because xn plus 1 is non-zero.
Can't be 1.
Right. Oh, wait a minute. Can't be 1.
'Cause it's not the
Oh, and that's the point we... Yeah, good. Alright. And so then we just have to take this and plug it back up in here, and there you have it. Sigma of x, right? And of course you notice that, so I mean it's best to plug it back into this formula basically. We have, what happens here? Something cute happens with the last thing when you plug it back in there, I forget. We work over here. I have t, well I have t times xn plus 1, right? Minus 1 plus 1. If I set, oh, I'm an idiot. What a stooge. Let's see here, so, just dumb. Sorry guys. What's the n plus 1th coordinate in the mapping we're trying to construct?
0.
0. And that is true because that was how we constructed it. Idiot. So this is the t that is here and here and here and so forth. So if you wanted me to write it explicitly, we could write it like this: 1 over 1 minus x to the n plus 1 times x1 xn and then 0. Yeah. And there you have it. That's explicitly the formula for stereographic projection. Is that a homeomorphism? It's fairly clear from the sort of heuristic picture I drew that it's injective. But you could actually invert the formula, all right, if we have more time, or if I wanted to. And, and it's also continuous, right? Because we're looking at a rational function of coordinates where the division by 0 doesn't happen by construction. So there you go. That is why an n sphere with the north pole deleted is homeomorphic to Rn. Right? Okay, so just a specific calculation. And that leads us to a discussion of Brouwer's fixed point theorem. Actually, that doesn't really have much to do with Brouwer's fixed point theorem specifically, except that it involves some of the same spaces, same nomenclature. Okay, so we get to it. And so, basically the point of this section, right, is what he wants to do in this introductory section is to just sort of showcase what algebraic topology does, how it works, and how some of the, because we're going to have to work fairly hard to develop some of these things. We're just pulling from the thin air in this section. But the application here is actually, of course, quite interesting. So we just try to sketch the application here. So this is here for, first of all, the fixed point theorem. Let me just say what it is. If this is Brouwer's fixed point theorem. Nathan, you know who Brouwer was, don't you?
Yep.
Is he dead yet?
I think so.
Yeah, it seems likely. He was, in terms of philosophy, what did...
He was one of the founders of intuitionism, actually.
yeah, that's right. So he's the one that gave up on the contradiction?
Contradiction? No.
No? Who am I thinking of?
Well, you're not thinking of anyone that I know of.
Okay.
You're probably just misinterpreting intuitionism.
That's exactly the kind of answer I'd expect from you, Nathan. Very good. All right, F from DN. Being a Trump supporter, of course, I don't appreciate nuance. Or am I a Trump supporter? I don't know.
He rejected the law of the excluded middle.
Let's see, your F continues. I'm sorry, I'm distracted from my own thoughts. But yeah, he, of course, is an important... I mean, this deep theorem I'm stating, he did when he was about your age. And then he got distracted, I think. Anyway, this continuous. Eventually, I'll teach math history and settle all these things, but you know, it's gonna be a while.
Until then, it's fun to make up stories.
Until then, we just make up stories. Yeah, I like that. Be like Mr. Rogers. Won't you be my neighbor? Let's see here. Maybe you guys don't know about Mr. Rogers and his Neighborhood of Make Believe.
It's a long time ago.
It's a long time ago. Have you watched Mr. Rogers' Neighborhood of Make Believe?
I think so.
Haven't
Okay.
watched it.
That's a long time ago.
Oh, so it is important for your mathematical development. I mean, this can't be a coincidence. Both of you watched it. I bet if I quiz Calculus 2, less of them have.
Probably.
It's probably
That's
Yeah.
definitely.
it's probably part of the problem.
Probably on the edge.
Let's see here. All right, so continuous function from the end disk to the end disk. Then there exists x in the end disk for which f of x equals to x. All right? In other words, there's a fixed point. So he gives a proof in here on page 3, which you'll eventually be able to look at, which is based on some sort of diagonal argument, looking at the diagonal that goes from like -1 to 1, 1, and some little slick little continuity argument. Basically, he shows that if it isn't the case, it gives you a separation, but that contradicts the obvious connectedness of the set, and so there has to be a fixed point. But then he goes on to say that nobody knows how to adapt this elementary topological argument for n larger than 1. So he says there's a proof using simplicial approximation theorem by Hirsch, and there are proofs by analysis, Dunford and Schwartz. Dunford and Schwartz is like a functional analysis book. So that's kind of like what? He tells us a little bit later in the section that in fact the fixed point theorem is also known for infinite dimensional spaces. And so that's in Dunford and Schwartz. There's a given, you need a little bit more, you need some, it's not dn anymore, it's a sufficient infinite dimensional cousin of dn for which the theorem still holds. I can tell you in a second. It's like a whole page ahead. An infinite, you need a compact convex subset of a Banach space. Continuous mapping from a compact convex subset of a Banach space to itself has a fixed point. Anyway, so here's how this goes. Basically what we do is you're able to use the homology functor. So what's a homology functor? Homology functor. So essentially it's this. If I have a function, a continuous function, from a topological space X to a topological space Y, the homology functor, it allows me to do this. It says that there's, well, Hn of f, all right, gives me a mapping between the homology, the nth homology of X to the nth homology of Y. So the homology functor induces maps on these algebraic objects, these homology groups, on the basis of a continuous function. And more than that, it also respects composition in the following way. So this is a homomorphism. So basically we're trading a homeomorphism. Well, excuse me. Continuous map. I don't know, we don't, that's annoying, right? We call it continuous. It would be nice if we called it like, there should be some kind of morphism there, but we call it continuous. It's, you know.
Topological morphism?
Yeah, topological morphism, but that is not what we say. It's a continuous map and it induces a homomorphism. And also, it has the following property, categorical property. G composed with F. The homology functor of G composed with F is the
Composition.
yeah, come on. And so I guess Nathan, you probably already can tell me what kind of functor this is.
What kind of functor it is?
this is a contravariant functor or a covariant? Is that a reasonable thing to even
Oh,
talk about?
yeah, that's, if it were contravariant, that would be reversed.
So this is it covariant?
Yeah.
Okay. I think we get to that like maybe Thursday, some of the basic jibber jabber about category theory. Nathan is by now distrustful of my comments on category theory. I've talked to him enough about it. He knows I know nothing. Let's see here. Hn of the identity function on x, all right, is equal to the identity function on Hn of x, all right. So like the homology functor takes the identity function to the identity function, among other things. All right, so as I mentioned, we should cut it short today so we can fill out meaningless paperwork. Let's see here. When is it we're supposed to end at when? Like 3? What? 3:30?
25.
Okay, so I'm going to try to end at 3 today, so we still have. We should have 25 minutes should be enough to explain why you guys are worthy. You know, the usual bragging. Here. Okay, so in particular, we'll calculate. You can calculate. We haven't done it yet, but with sufficient. I mean, this obviously begs questions, right? Like, how do you construct these homology groups, right? We'll spend a while explaining how that's done, right? There are different schemes, simplicial homology or singular homology. Then there's like, well, I mean, focus. There's a lot of different ways to do things. Yeah. So. But, oh, I don't need this anymore. I mean, this is a great example of just how nice Rotman's book is. Like, look at how concise and clear his derivation of the stereographic projection map is there. I mean, it's not just like, I'm just going to throw it in there and I'll waste the reader's time with 2 pages of kind of like just lackadaisical calculation. No, I mean, it's to the point, right? It's a great derivation. I'm sure it's in other books, but I just appreciated it. I don't know.
Yeah, I don't remember. I saw the derivation of that formula somewhere else before, and it just wasn't quite as nice as this. Like, when I read that in Rotman, it was the first time I really understood it.
Exactly. I think that's going to happen a lot. Well, I don't know how much that can happen if you haven't read algebraic topology before, but so okay. So where was I? So in particular, we can calculate that the nth homology group of the n+1 disk is 0 for n greater than or equal to 1. In other words, for n a natural number, Nathan. Now, Hn, and Nathan's like, I wouldn't disagree. It's almost all the natural numbers. Yeah, fine. They're trying to make 3 a variable in PDEs that the ghost of Joe lives on. Let's see here. The nth homology group of Sn is not equal to 0 for n greater or equal to 1. All right. And so basically using these known results, all right, from when? From the future, of course, all right. You can show that there can't be a fixed point. Let's see here, let me... all right, so we need a definition. Definition. And I think we talked about this some last semester, but it's good to review. A subspace X of a topological space Y is a retract of Y. So X subset of Y is a retract of Y. If what? If a subset V of X is open, is open if and only if V is equal to the intersection of X with some open subset U of Y. Let's see here. I think he says, observe this guarantees that the inclusion map is continuous. For a retract, right? Because the inverse image of an open set in Y, right, under this map is necessarily, well, it's by definition open, I suppose, up here. I'm sorry, I'm trying not to cough in here. Enough of us are sick already.
Because the inverse image of a set in Y would just be X intercept Y. Right. Like the inverse of the inclusion is just kind of like, is it the intersection? I'm trying to remember.
Well, inverse image of X intercept U is inverse image X intercept inverse image of U, right?
So you're, so you're,
and then that gives,
right,
those are both open, so.
well, I don't know, sorry. Unnecessary writing, excuse me. Oh, okay, so, getting to the point here. Basically, the point is for a retract, the inclusion's continuous, and he says this parallels group theory. He says a group H is contained in a group G as a subgroup, if and only if the inclusion is a homomorphism. So H, subset of G, right, is subgroup, if and only if the inclusion map of H into G is homomorphism. I don't know if we probably haven't thought of it that way that much, but
I mean, it just means it has the same structure.
right. I mean, we usually, I mean, in the introductory course, we usually think about subgroups in terms of like, you know, elements and closing, but that's how to capture the notion in terms of maps, I think.
I guess that's a homework problem.
Yeah.
Or you could say that the subgroup itself is that homomorphism.
Oh, that's not any homomorphism. That's also the inclusion, right? So.
Right.
So the, I mean the.
By category, in category theory, a subobject of an object is just an epimorphism, or no, monomorphism into that object. So they're actually identified in that case.
I think you're getting into a future chapter now, but I'll allow it. Let's see here. Where are we? So, in any event, just to get to the point here, a continuous map R from Y to X is retraction if and only if the composite of R with the inclusion map is just the identity on X. Or I think he says 1X. So, I mean, you could, and I have seen that taken as a definition in other places. But, So, his point number 3 is for abelian groups, you can prove that a subgroup H of G is a retract of G. If and only if H is a direct summand of G, that means that there's another subgroup K, which intersects G only at the 0, and K plus H is equal to G. That's exercise 1. Yeah. I would like to just not teach Calc 2 today and do that exercise, but I might get in trouble. So I better not. But if I were you, I might do it. I don't know. But I probably should study for the GRE. I don't know. Yeah. Choices. All right. So here's the lemma. Lemma is this: if n is greater than or equal to 0, then Sn is not a retract of dn plus 1, the n plus 1 disk. I think I can do it over here. So we start with we suppose that there were, all right. Suppose that R from dn plus 1 to Sn, right? Let's see here. So this, in order for this to, this is all in the context of what? X being a subset of Y, right? Okay, so
Does there have to be a retract for there to be a retraction?
what?
Does X have to be a retract of Y? Like, for the definition of a retraction, is that assuming that X is a retract of Y?
I mean, the existence of this R makes X a retract is the point. Yeah. I mean, I do think that you need X to be a subset of Y as a precondition of this definition. But I think from this data, it follows that X is a retract. In other words, it's an equivalent statement to this up here, if I remember right. So does that make sense? I mean, is Sn a subset of the n plus 1 disk? Yeah. Okay. So that at least is the right kind of thing to do. And he says, if there were a retraction, we could draw the following commutative diagram of topological spaces in continuous maps. So what he does is he's like, okay, so you got this sort of, you got Sn, you got Sn. Of course, what map do you have on Sn?
The identity.
Right, you have the identity. And then, well, you have the inclusion map here, right? The inclusion of Sn into the n plus 1 disk there. And then, allegedly, you would have the retraction map here. Now we're hoping that this leads to some absurdity. All right. So then what you do is you feed this diagram to the homology functor, and out pops a new diagram in terms of algebraic objects, right? So from this diagram, after you feed it to the homology functor, what do you get? You get the nth homology of dn plus 1. And down here, of course, you get the nth homology of Sn. You get the nth homology of Sn. The homology functor, of course, takes, I mean, this is just, again, the identity map down here, right? He uses a different notation, but I'll use that. And here you have, goodness gracious, the homology functor of the retract, and And here you have the homology functor of the inclusion. All right. But the thing is, right? What? He says by property. He says by property one of the homology function. No, this diagram commutes. All right. What's that mean?
R composed with I equals the identity.
Yeah, we can choose our own adventure, right? Yeah. Would you say R composed with I
Yeah.
equals the identity? Right. That's essentially the. I mean that is the existence of the retraction, right? But part of the homology functor is that it takes a commuting diagram to a commuting diagram. So we should also have what over here then? I guess we get Hn R composed with Hn I equals to the identity, right? All right. But since the nth homology group of Dn plus 1 equal to 0, remember this up here? What does that tell us? Now he says he's referring to part 3, the abelian group thing I mentioned before, which was that if H is a subgroup of G, H is a retract of G, if and only if H plus K is equal to G and H intersect K is just the 0. Here, we're talking about an abelian group. The homology groups are going to be Z modules, so they're abelian groups. But anyway,
H sub n of I has to be the zero morphism, right? That sends everything to 0 because that's all there is. So then you compose that with H sub n of R. That has to also send everything to 0 because it's homomorphism. But then that can't possibly be the identity.
How do you getting at?
So H sub n of I
Yeah.
must be the 0 homomorphism because H sub n of Dn plus 1 is just 0. 0 is all there is.
I'm sorry. That makes sense what you're saying. Since this is equal, I mean, there's probably a couple different ways to think about this.
Yeah.
I think we can think about it without this, actually, if you want to, from what you're saying. I like what you're saying. So let me just... Doubtless what Rotman says is useful and probably the right way to understand it, but this is also good. So you're like, that's 0. So if this is a homomorphism
Right.
that's mapping into a space which is 0, it's the 0 homomorphism.
Yeah, then if you take another homomorphism of that, it has to be 0.
So so the fact that this is 0 basically forces the whole thing to be 0.
Right.
But that's not 0, which is a contradiction. Very good. Yeah. So there can't be a retract. Very good. So what does that have to do with the fixed point theorem? Right? So here it is. You just mostly just draw a picture. And so basically, to contradict this, suppose, f of x is not equal to x for all x in Dn, right? Then you can draw the picture like this, as he does, on page 5, f of x, right? And let that be g of x, right? He says the distinct points x and f of x thus determine a line. True, right? You can do this for any x, right?
Right.
Any choice of x. F of x is another point. They're distinct. They determine a line. And by the way, they're also both in Dn by construction, by assumption. So they determine a line in Dn, and lines in Dn don't stay in Dn forever. Eventually they hit the edge. You could prove this, but the picture suffices. And so you define G to be the g of x by the picture, right? G of x is the point of intersection determined by x and f of x to reach x. All right, and he says, okay, well, what does that tell us? So, is gx, what is gx?
It's mapping from, yeah, so it's an Sn minus 1.
All right.
Not
So-
a retract.
I think it's more fun
Not
if
a
we.
retraction.
It's kind of more fun if we do this, right? It's a little bit more obvious. Yeah. Just to match the lemma. Oh, shut up. Oh, her battery's low. Because it's not quite that yet. We're still 3 minutes. Anyway. Let's see here. I mean, that picture is very abstract, but reasonable, right? I mean, it's like the one I had here earlier. The Sn being the sort of equator of the n+1 ball. All right. Then what is he going to say? Well, he says, obviously, if you have x an element of Sn minus 1, that implies g of x equals to x. So this g function, right? What happens? Yeah, well, yeah, okay, right.
Okay, if x
Yeah.
Right? Is that's actually pretty obvious, right? Yeah, from the definition that we stated.
Mm.
So that means that g is a retract.
Yeah, a retraction.
It remains, of course, to prove that that mapping is continuous.
Right.
But it's fairly obvious that it is by analytic geometry, right? Because we're talking about lines intersecting circles, and so through a calculation similar to the one we did earlier today, it should give us rational functions of the coordinates involved with no bad divisions by 0. There's some details to be fleshed out here, but it's fairly clear that that's a retract. But that's impossible! Therefore, there exists a fixed point. And that is an example of the power of algebraic topology to prove things which are otherwise, well, I don't know, I guess unprovable. I mean, I think, that was part of what attracted, I mean, if all topology was just abstract nonsense, it would still attract, like so many moths to a flame, pure mathematicians, right? But it's more than that. It's solved problems that were standing and were insolvable before. And more recently, topology, even algebraic topology, has begun to be applied to electronics and quantum mechanics and things. We're really just at the genesis of that. I don't think I even know what's current anymore. So, anyway, I think that's a good start. I'm going to hit it. And get off here. Thanks, guys.